So in the next part of the tutorial, what we will see is how to construct an initial volume. So for an initial volume, we have taken the center particles, and these center particles are around 3500, and then we will use different algorithms. We have again for the initial volume, we have many of them, and if you install all the plugins, you have even more. And then they try to figure out how the particle looks like based on these images and classes. And there are different mathematical rationales behind, and some of them are based on maximum likelihood, some others are based on robust statistics, and well, they have different ideas. And the point is that the initial volume absolutely drives the reconstruction process. So sometimes if you have a good initial volume, that is fine, but if you have a bad initial volume, sometimes it can escape from that local minimum, and sometimes it cannot, and it will produce very bad reconstructions. One of the indications that you have a bad initial volume is when you have good looking 2D classes. So the quality of the 2D classes gives you already, so here we see high frequency, relatively high frequency details, and when you cannot reach high frequency in 3D, when you see high frequency details in 2D. So for instance, here we have used the cryospark. Most of the most important parameter in most of these algorithms is what are the particles and how many classes you have, and the symmetry of that class of that object. So we will construct a single class and with octahedral symmetry, and then the remaining normally it doesn't matter. And here for instance, Ransack, instead of the images, it is using the classes, so the representatives of those classes, and Relion is using the images again. So here we are using these images, and we are asking again for just one class. All the remaining normally you can keep the same. And here is the symmetry for Relion. Those are the most important parameters. So which are the images, how many classes you want to reconstruct, and what is the symmetry of that particle. And reconstruct significant is working on the set of classes again. Okay, so then for instance we can look at the different results. So sometimes it is very obvious to see that there is some mistake in that initial volume. So for instance, this one doesn't look quite good. So for some reason Chimera doesn't work on my computer, so probably well, we can do it. So for instance, this one, so sometimes it is hard to say whether it is good one or not. So for some reason it didn't like the cryospark one. So this is not really a good one. It is not too bad, but it is not really the structure that we are looking at. And then for instance, this is Ransack, this is Relion initial volume. So for Relion we have something that looks a bit better, so at least it has high frequency details, and yeah, so, and it has Apoferritin has these 4 squares that or this square with 4 corners, and this is something that we should look at to see if we can find it or not. And yeah, but it is very low resolution, for instance, and for significant we can also see, I think, these 4 corners. So we see 1, 2, 3, so we see the 4 corners, and but you see that the internal details of the structures, they look rather different between significant and rely on, and the different initial volume algorithms. So different algorithms at the end, they have different properties and they produce different results, and not always there is not a single algorithm that will work always at for all sizes. One of the particularities of the initial volume of CryoSpark is that it produces one that is smaller than the input particles, so you have to resize it, and for resizing it is useful to do so you take the input volume, you want to change the sampling rate from 2.32 to 1.24, and the box size is automatically determined, but sometimes there is 1 pixel error, so it may produce, for instance, let's say 119 voxels volume, and you want it to be 120, so you can also at the same time apply a window operation and enlarge it to 120. There are some other options like cropping, so you can crop by a given amount of pixels from the borders. Okay, so once you have all of them at the same size, so all these volumes are at 120, we align them. So the alignment of the volumes, it serves for 2 purposes. One is they all more or less line the same orientation, so that the next algorithm will have a better time, and it finds it easier to align the different algorithms, the different volumes. And the other one is that for the next algorithm we need a set of volumes, and the way to construct a set of volumes, or one possible way to construct a set of volumes, is by aligning all of them, and then the output will be a set of volumes. And actually that is why you use a reference, that is in this case reconstruct significant, but that reference is also part of the volumes that you want to align, because otherwise it wouldn't be in the output set. And then here we take all the different objects that we want to align. Something important is that you choose the fast Fourier as the algorithm for alignment, because otherwise it may take too long if you use the exhaustive search. Or local is when you think that the 2 volumes or the set of volumes are relatively aligned and you just want to refine the alignment, and you have also this possibility of exhaustive followed by local. Okay, so we chose fast Fourier, and then the output of this is a set of volumes that are more or less in the same orientation, and for some of them we have the label where it is coming from. Some of them they don't produce this label, so this is the one of CryoSpark, this is the one of Relion, and these are the ones of Ransack. And then you enter into the swarm consensus. So the swarm consensus is another one of these nice things of having everything together into one single platform. That is, you can take the input images, you can take the set of volumes that are candidates, and then you can try to find the commonalities and to let them evolve. So this algorithm is thinking of the input volumes as a swarm of candidates, and then it lets the swarm evolve trying to match the input images. And you can also add a mask. In case there are some cases in which you really need to constrain the search, and that is why you provide a mask for the volume. But at this point, probably you don't know really how to construct a mask, and also it is by masking you may be losing part of the artifacts that are outside. So if the if the output is not good, then it will have artifacts outside and you will not be able to see them because they have been masked out. So this is the output. So you can see that it is low resolution, no doubt about that, but it has the right shape. So it has these four corners that we know our structure has. But these four corners, they have been automatically chosen among all the possibilities. So you saw that there were kind of 13 volumes at the input. So there were 13 volumes at the input. Only 2 of them have these four corners, and the algorithm has been able to decide that these four corners are the right property of this structure. And very often it produces the right results. Doesn't mean that always will produce the best results. And this set of volumes here, it has actually, I think, some columns. No, not this one. Okay, sorry. I thought that the set of volumes, internally it is calculating some parameters to decide which one is good, which one is bad, and I thought it was exported to the set of volumes, but it is not. Okay, so then at this point we have an initial volume that has been automatically chosen among different proposals. Many of them, they were not the right thing, and then we have extracted from the previous step. We had extracted the particles that were not duplicates, that had passed through all our picking and 2D filtering process. And something important to comment here is what is the size of the output. So we said that we have a data set that is practically limited in this case because of the beam tilt correction to around 2-3 angstroms resolution. So Nyquist for 2 angstrom resolution is 1. So we should extract at least at 1 angstrom per pixel. We have done it a bit smaller, and then let me copy it. So let's say that I have applied a downsampled factor of 1.5. That is the one that gives this 0.74 angstrom per pixel. But if you apply just that factor, then the number of pixels is 200. So this 200 is the one that corresponds to the 300 box size that we chose when picking the particles. But we said that if we want to correct for the CTF effects, we needed to have a wider view so that we can effectively invert the spread of the point spread function. That is why instead of 200 I have chosen 250. So 250 is 50 pixels more, and these 50 pixels in 0.74 angstrom per pixel gives you around 30 something extra angstroms. That is actually more or less the size of the PSF. So the longer the delocalization of the information caused by the PSF, the bigger should be your box size, so that you can collect all that delocalized information and put it back into the 3D structure. So that is why I have chosen 250. Okay, so anyway, in this particular case we will not reach extremely high resolution. So it is not that we don't care, but it is that we cannot really achieve such a high resolution. So all these very little details cannot be correctly compensated. And here the swarm consensus produced the volume that was at a different pixel size that the extracted particles. So we will apply the same crop resize volume, and this 2/3 means that is at a size that is 2/3 of the original size. So so here what we have is you take the input volume, you change the sampling rate, and you change the window so that it fits the one from the extracted particles. So at this point in the workflow, what we have is a set of particles extracted at a particular size, and then an initial volume at a similar size. So let's stop here, and then in the next part of the tutorial we will try to clean, but now in 3D, this set of particles, and then make a 3D reconstruction out of it.